So Aaron, whenever you're ready, take it away.
Thanks, Jessica. Yeah, hi everyone. For those that I have not had the pleasure of meeting, again, I'm Aaron Hill. I'm a research scientist at Colorado State University, working in Russ Schumacher's group. I've been here about 3 years now, working on this task of developing products, machine learning products for these high impact weather scenarios, and specifically how we can leverage that for operations in the National Weather Service and at operational forecast centers. So I probably don't need to motivate this too much, how machine learning is being a little bit more prevalent in weather forecasting lately. You all have probably heard about it ad nauseum, but one of the ways that it's being leveraged is to post-process these large data sets that we're generating from models. As an example, using machine learning to emulate or to mimic operational products being put out by the Storm Prediction Center or Weather Prediction Center. And I threw an example here on the left of on the bottom, the operational product from the Weather Prediction Center. If you're unfamiliar, this is an excessive rainfall outlook, so 24-hour forecast of where they expect excessive rainfall. But we can generate a similar product from a machine learning model that essentially mimics what WPC would put out there, both probabilistically as well as spatially. And so these are particularly valuable as what we have termed first guess fields, a first snapshot look at what some of these products should look like. Obviously, we're developing these based off the GEFS model, which I'll get into in just a little bit. But there are other groups at the National Severe Storms Laboratory developing these systems off the HREF, Eric Loken there at NSSL, as well as Ryan Sobash at NCAR, developing similar systems with the HER. And so one of the questions you might ask is, why bother with machine learning? We have these sophisticated models, we have convection allowing models, we have other post-processing tools, but in some sense, machine learning offers an opportunity to do some of these tasks a little bit better. For instance, we don't specifically forecast convection hazards. We can't simulate a tornado in our operational models. We have to use some kind of proxy.
Aaron,
Yeah.
Aaron, I'm wondering, it might just be me, but I only see your title slide still. Is that what you want to be on?
Oh, no, it's definitely not. No. Let me try this again. Yeah.
Now I can see the why machine learning slide.
Hey, okay, so this is the slide I was just talking about. Thanks, Kenzie. I'll go over this again. This example here on the left, this is the first guess on the top and the ERO on the bottom. So I won't say everything I just did, but you can see the similarities there spatially. The probabilities are aligned, and so the forecaster might look at this and say, oh, there's a high probability of rainfall up in the Northeast. This is from Hurricane Ida as an example. And so they might have more confidence in going with a moderate or high risk as a result. So, so why machine learning? Again, we don't explicitly forecast these hazards, so it's an opportunity to do something better. In other ways, you can use machine learning to speed up our models, do something faster. For instance, radiation code is pretty slow. And there are other research groups trying to implement machine learning within the models themselves. And then there are other research groups trying to essentially elucidate new relationships that might exist in our dynamical system that we didn't know existed. And so machine learning is a valuable tool and can do a lot of these things really well. And one of the points I like to make is the fact that machine learning is not this black box idea anymore. Within our kind of geophysical and meteorological fields, there used to be this idea that we didn't know what was going on inside that black box. We didn't know why predictions were being made. And that's not necessarily the case anymore. There's a lot of work being done within the last 5 years to really make these systems interpretable and configurable and allow us to understand what's going on. And I refer you all, if you're interested in reading Amy McGovern's paper in Banff from just a couple years ago, that really highlights how these models are really a lot more interpretable than they used to be. So within our group here, we focused primarily on excessive rainfall and severe weather, that being tornado, hail, wind. And as I mentioned, NWP models don't explicitly predict these. We have QPF for models, but that doesn't necessarily tell us whether rainfall is going to be excessive or whether there'll be downstream impacts like flash flooding. For severe hazards like tornado, hail, and wind, we have to use proxies, for instance, updraft helicity. Again, good proxies, but it's not an explicit prediction. But for machine learning, what we really want is a long record of observations and long records of, predictors or environmental fields that relate to those observations. And we have those now. We have long records of tornadoes and hail and wind, and we can create long records of excessive rainfall. So really what we needed was long records of the model simulations or environments that relate to those observations. And with the new GEFS reforecast system, this really is an opportunity for us to do something better, that first bullet point for machine learning. As I mentioned, one of the reasons that we're trying to do this is the operational benefit of first guesses. And I highlight some of these results from a paper a couple years ago that we published on a severe weather prediction system. This is a Breyer skill score, so it's a measure of skill for day 1, day 2, and day 3 severe weather forecasts. And the only thing I'll mention here is at day 1, the SPC is routinely better than the machine learning models, but when you combine those two in a kind of a blended way, the blend itself, which kind of acts like you're inserting the machine learning guidance into the human-based forecast, that blend outperforms either of the individual components. And so we motivated this idea that if SPC specifically was ingesting machine learning products into their forecast process, they could be improving their day 1 forecasts. And we saw that the skill of both the blend as well as the machine learning models was better than SPC forecasts at day 2 and 3, which kind of motivated going beyond that too. For excessive rainfall, we see similar things at day 1. The WPC forecasters are better than our machine learning models, but we start to encroach on their skill at days 2 and 3 with these different models. The machine learning models are these different colors, where WPC is yellow. And we've been making, iterative improvements on these systems since 2017, primarily through the hydrometeorological testbed flash flood and intense rainfall experiment. So really, we've focused on developing these systems, but also making them operationally relevant. So much so that we've actually operationalized a few of these that are now at WPC running on their local computers so that forecasters can use them on a regular basis. I'll also mention that we've started getting into medium range products, medium range being like day 4 to 8. Obviously, convection allowing models or CAMs, they don't go beyond day 3. They're somewhat limited in that respect, just in some ways just because of computation. And so we have deterministic global models, GFS, the European models. Those are great. We have some global ensembles, but there's also limited post-processing. And I mentioned that because the ensemble mean or ensemble spread doesn't provide a lot of confidence on convection hazards. Maybe it provides confidence on temperature or general locations of where severe weather might exist, but specific hazards it doesn't. So back in 2020, the GEFS was upgraded to the FE3. So we had a bunch of prior machine learning models developed on the old GEFS, and we needed to retrain those and redevelop them based off this new FE3 GEFS. And so what I'll kind of talk about here in the next few slides is that development, how random forests work, which is our primary machine learning model. And then I'll get into some like early results of these new models and how skillful they are and how we can better inform operations and better help forecasters deliver operational products. Okay, so if you're unfamiliar with machine learning, again, we use random forests, which fall under the umbrella of supervised learning, and I'll kind of go into what these are. So in the meteorological realm, you could imagine a grid of points, and you want to make a forecast at this red point here. Let's see, Can you see my cursor, Kenzie, or anybody else?
Yes, we can.
Okay, awesome. Thank you. So if we want to make a forecast at this point, you might consider the meteorological predictors around that point, both in time and in space. You might ask questions like, what's the temperature over here? Is it greater than 20 degrees Celsius? What's the CAPE at this point? Is it greater than 500 joules per kilogram? And you can ask a series of questions which allow you to traverse these different branches of a tree. And once you get to the bottom of the tree, this can give you some answer of whether you're going to see excessive rainfall or whether you're going to have severe hail. And the aggregation across each of these trees over, for instance, a forest of trees can give you a probabilistic prediction of a hazard. And so in our setup, what we do is we train models for different regions of the country based on climatological frequency of hazards. For instance, when we build our severe model, generally west of the Rockies or west of the Continental Divide, we have a generally climatologically homogeneous severe storm environment. So we train a model there. We have a central US model as well as an eastern US model. And we take that approach where each model is trained using this kind of forecast point relative framework. So we grid all of our observations across the Western region. We associate each of those observations with guess predictors, and then we can train over a really long period of time. And so these are an example of some of the predictors that we use: accumulated precipitation, CAPE, SIN, sea level pressure, 2-meter relative humidity, shear values, storm relative velocity. Again, all variables that we would expect to be associated with severe weather, whether that's excessive rainfall or tornado, hails, or wind. And I've kind of I've thrown in some text of how we set up our model. I don't really want to get into that too much. It's just a lot of the nitty-gritty details. We have some papers that kind of go over this. But I'll mention that the setup here is mostly convection hazard agnostic. So we train the excessive rainfall models in a very, very similar way to how we train a tornado model or a hail model. And all of the models essentially create forecasts over these 24-hour windows that are analogous to the operational product. So if you're forecasting day 1 hail from 12 to 12 UTC, the forecast that we're providing is a 24-hour probability of hail. And if you like graphical representations, this is another way to kind of visualize how we train. So we take this kind of spatial frequency predictors, but we also have temporal frequency. So you can kind of think of an event, you know, a hail local storm report at this red dot, but we want to know how the environment evolves over space and time over that 24-hour window. So it's like a 2-dimensional time series when a hail report is recorded in that 24-hour window. We do that for all of the meteorological variables and over every single point in space across the CONUS and over long periods of time. So we're talking about multi-million points of events, but also 6,000 plus predictors per point of training. So lots and lots of data that are going into the random forest model. And what we can do is then throw some real-time model output from the operational guests and create forecasts. So I obviously can't cover everything we do with excessive rainfall and tornado, hail, and wind models. So I'm just going to focus for brevity on our severe weather prediction system. If you're interested in the excessive rainfall, Russ and I co-authored a paper with collaborators from WPC last year in BAMS, which I'm particularly proud of because it really highlights the success of this transition from research to operations and these iterative improvements to our models and how that can be leveraged for operations, but also put into operations. So I do orient you to that paper, and I'm happy to share that with you if you would like it. So for severe models, we make direct comparisons to SPC. Obviously, there is no other kind of good product. We can create forecasts from, say, updraft velocity, but in reality, we want to know how these machine learning forecasts compare to the human forecasters. And one of the first ways we do that is looking at how often we issue forecasts. So up at the top is the day 1 hail, shows a 15% contour frequency, and then the bottom is the day 3, 15% And as a reminder, day 3 is any severe probability. So it's a slightly different product. It's not individual hazards. But this is just kind of a first glance to see, are we issuing forecasts at the same frequency as SPC? And you'll see at day 1, that's generally the case across the CONUS. We have a very similar distribution of these contours. Where we see differences start to emerge are at day 3 and beyond, where we see SPC is issuing less frequent forecasts, a little bit more conservative, while the random forest system is essentially issuing forecasts whenever it wants, however it wants. There's no restriction, no stipulation. And where you might have in operations, differences between forecasters or actual considerations of continuity between a day 4 outlook, a day 3, and a day 2, the random forest system doesn't care. And so it's issuing forecasts a lot more frequently, which oftentimes means it has more skill. And we see that quite a bit. Here on the left, again, is the Breyer skill score. For the most part, these first 3 are the day 1. The second 3 columns are day 2. And this last one is day 3. So you'll see at day 1, the purple column, which is SPC forecasters, generally either equivalent or slightly better than the random forest. At day 2, that's mostly the case except for the wind prediction, but at day 3, the random forest is better than SPC again. And over on the right, this is area under the rock curve, which is a measure of resolution, how well the forecasts are able to delineate reports from non-reports or observations from non-observations. And so generally, we see that at day 1, SPC and the machine learning products are very similar, but those similarities start to decrease, and there's a lot more separation between the 2 systems and 2 outlooks at days 2 and day 3. And so the random forest system is able to delineate where events are happening slightly better than SPC. And that's kind of an aggregate perspective. And one of the things as I mentioned with the excessive rainfall forecast with FAIR, one of the important aspects of evaluating these systems is getting human eyes to look at it. And not just SPC forecasters, but NWS forecasters, researchers. And so last year, as well as this spring in 2022, we started introducing these products into the hazardous weather testbed spring forecast experiments, where we essentially evaluate these products on a daily basis. So forecasters and researchers can look at, for instance, our forecasts up in the top right as it relates to other systems like this HER-based system or an href calibrated product, and as well as how that relates to the observational distributions. And so we can rate those and see how people perceive them. And so last year, we had subjective evaluations that participants that felt our day 1 guidance actually had the best skill, which somewhat is surprising for us because the guess is a little coarse, and you would expect that maybe a CAM-based system or the raw output from a CAM would perform slightly better, but that wasn't necessarily the case. And that was similarly true at day 1. Now, I will mention that we're not comparing these systems against SPC, so they're just rated against other experimental products. But this was very encouraging for us going forward as we're developing these systems more. We also like to look at skill kind of in a spatial sense and evaluate, where is their value relative to the other areas. SPC, this is a day 2 wind forecast. SPC generally has a lot of positive skill east of the Rockies. There's some small events here and there, mainly where maybe observations didn't exist, but a forecast was issued that maybe make this appear like they have a poor skill in some areas. I'll also mention our verification period is only about 1.5 years right now. The FE3 guess became operational in October 2020, so we only have about 1.5 years worth of forecasts to evaluate. So there's some kind of a caveat there. But in general, we see that the spatial skill of the random forest matches that of SPC, and that's something that is particularly good to see because we want forecasters to see value in these systems, but also be able to trust these systems. If we look at day 3, SPC is almost uniformly positive east of the Rockies, but also the random forest in an aggregate sense is slightly better. This is largely because there's some a lack of confidence in issuing some day 3 forecasts by SPC forecasters, as I mentioned before, but also that the random forest kind of can issue a continuous slate of probabilities. So perhaps where SPC only wants to issue a 5, the random forest can bump that up to a 9, for instance, and have slightly better skill. So I don't want to nitpick on some of these smaller values, but in an aggregate sense, we'd like to see that these two are really comparable. So that was on the shorter range. I do want to highlight some of our medium range products, which are very new, something that we've developed within the last 6 months. So this is an example from a case back in mid-December of 2021, an event across the upper Midwest and into the Appalachians. And you'll see the storm reports as these blue and red and green dots with the colored contours as the probability of the random forest. I just wanted to throw this out there to show the kind of consistency across times. While day 8, the forecast from the random forest was only a 5% across the Southeast, clearly where there were no observations. As you approach day 6, the forecast is clearly highlighting that corridor really well. The probabilities are not high enough clearly, but the system has located where that event occurred. And so we've started to do some initial analysis of how these forecasts perform. Again, we want to look at frequency first. How is SPC issuing forecasts at these lead times? Where there was maybe a underconfidence bias at day 3, that's going to show up even more at day 4 through 8. And this kind of illustrates that SPC only issues 15 and 30% contours at these lead times. And so I've only showed the 15 here on the left at day 4 and 5. Clearly, over this year and a half, these forecasts are not issued that often. Whereas in the random forest, we can issue those really frequently, and that's going to impact skill quite a bit. This is the seasonal distribution. These colors are the different days, the forecast days. On the x-axis is the months. The top row is the 15% contour, and the bottom is the 30% contour. And all I really wanted to show here is, while SPC does have a relative maximum in the spring season, as you might expect for 15% contours, and just a handful of 30% contours over the year and a half of verification, the random forest does not care about seasonality. And in fact, issues a relative maximum across the summer warm season, which is an interesting signal for us. And that at 30%, however, you get kind of a more climatologically representative distribution of these forecasts, which really focus in on the March, April, May season, as you would expect for severe weather. So when we aggregate skill for these longer range forecasts, we see that in this light blue is the random forest when you only use the 15 and 30% contours, so kind of a direct comparison with SPC. In the red bar is SPC. We see generally we can get skillful forecasts above a climatological reference of 0 out to day 6, loosely speaking. SPC is skillful at day 4 and maybe not as much days 5 through 8. And that's same for resolution. So we don't really have good resolution performance for either the random forest or the SPC at these lead times. However, when you consider the fact that the random forest has continuous probabilities and you start to throw in a 5% contour in these evaluations, what you see is dramatically better skill. So where the random forest and SPC are not performing well at higher probability thresholds, when you start to introduce maybe lower confidence forecasts or lower predictability events, the random forest does remarkably better, both in skill as well as resolution. And that's particularly important as a product that SPC forecasters might want to use. Again, spatial skill, this is the same Brier skill score map I showed before. Green is good skill, brown is bad skill, SPC here in the top, our machine learning system in the middle, and the differences. And all I really wanted to note here again is generally positive skill east of the Rockies. We don't have a lot of events in the West. I would not expect for these systems to do particularly well there, but we do see small differences across across the CONUS east of the Rockies, which are mainly just because of there's no events over verification period. So if you look at this little gap between Arkansas and Mississippi, this bottom plot is the frequency of days where we had a severe report over our verification period. So we have this relative min across Arkansas and Mississippi. That's where we also have a low skill. And up here in Minnesota, where we don't have a lot of reports, we also see poor skill. I'll also mention that this Brier skill score map is when we have a direct comparison between the two systems. So again, only 15 and 30% contours are going into the Brier skill score computation. When we use the lower probabilities, when we use a lower confidence forecast in these skill metrics, we get vastly improved forecasts for the random forest. Again, we still highlight areas where there are not many reports. Here in southern Texas, go back to here, there's relatively none over our verification period. And so we still are highlighting these areas that we really need a larger sample size to get a real good picture of skill. But generally, east of the Rockies, there's a lot of skill in these forecasts, even out to day 6, illustrating their value potentially in operations. Okay, I've kind of painted this picture that we have skill and that these forecasts are really good, but there's a lot to learn too. We have busts, and we need to understand where our forecast system does well and where it does bad. More often than not, where we see skill improvements are on low probability days, as I've kind of alluded to. So on the top right, we have this day 4 forecast, a 5% probability contour across the upper Midwest, not a high density of reports in blue, but SPC didn't have a forecast. And so their skill is going to look worse than our system. In actuality, what we normally see is that for high impact weather events, high probabilities are issued by the random forest, but also by SPC. And so the skill differences are not that high. Occasionally, and maybe I can count on my hand the amount of times that we've seen day 4 through 8 omissions from SPC, where the random forest is going 30 or 45% probabilities. This doesn't happen that often. And in fact, we also see incredible busts from our system. This is from, again, late December of 2021, forecast probabilities up to 30% across the upper Midwest. And you will see that there are no storm reports on this day. So at day 4, our system was saying there's a high probability of severe weather. And in fact, this little black tiny contour is a forecast of significant severe probability. So that's EF2 tornadoes or hail greater than 2 inches or winds greater than I want to say 75 miles per hour. And so this forecast is really bad, and we want to better understand why these forecasts happen and how we can fix those in the future. And that kind of dives us into this idea of interpretability of the forecast and explainability, something we've been working on more recently to interrogate, one, what the random forests are learning about our dynamic system, but also what meteorological variables are the random forests relying on to actually make real-time forecasts. So one of the first things we've started doing is trying to understand what the random forests are learning. I won't go into exactly how these plots are calculated, but these are what's called predictor importances. So where you have higher importance, these variables that are denoted on the x-axis here are considered more important to the random forest. So at day 4, you might notice that CAPE and SIN and 0 to 500 shear are the most important variables for severe weather prediction across the different regions too. It's a consistent signal across the different trained regions. But as you get to day 6 and day 8, you actually start to get a reversal or a change in predictor importances. You now notice that SIN is more important than CAPE. For some reasons, 2 meter specific humidity has replaced CAPE. And yes, there's probably a relationship between CAPE and specific humidity, but the random forests themselves are training and learning different relationships, but relationships that we would expect them to learn. But there's a lot of questions that we have about some of these signals and why they're happening and how they're feeding into the forecast that I don't have answers for yet, but it's something that we're moving towards. We also have some differently trained random forests, and I didn't want to go into those details a lot, but suffice it to say, rather than just taking predictors over the forecast period, we've also trained models that consider the local change to an environment before that forecast period. So training with prior day variables. And this allows us to see how a ramp up in thermodynamic or kinematic fields could be leveraged by the random forest to make better severe weather predictions. And while I didn't show it in this presentation, we should have a new paper submitted fairly soon that show these models that consider this prior day information are just as skillful as the models that only consider the information across the forecast window. And so there's some reasons for that and why that might be important. But in some ways, it's also nice to see that the random forest can learn these temporal relationships that we might expect. For instance, we talk a lot about how the Gulf might be quote unquote open to bring warm advection and more moisture into the Great Plains, which might support severe weather in coming days, or this idea that you can get a ramp up in the low-level thermodynamic fields would support that type of anecdotal evidence. And so again, relationships that we already understand, but the random forests are learning. That's something we want to see. Okay, so I kind of touched on how the random forests are learning relationships in training, but we also want to know what variables random forests are using when making forecasts, what they're using on a day-to-day basis. So there's this interpretability metric called tree interpreter, which essentially allows you to break down the probability of an event into the contribution from each meteorological predictor. So the sum of all those contributions gives you the probability. So what we can do is we can break down those contributions and aggregate them by variable to tell us which meteorological variable is contributing more often to real-time forecasts. So on the right here are violin plots. If you're unfamiliar with violin plots, that's great. I just started using them. I'm still learning a lot about them. What you can imagine though is this is a distribution of the frequency of the contributions for these different meteorological variables that I've outlined in green. So where you would see a really wide or really long distribution, you can ascertain that that variable is being used often, either positively or negatively towards the forecast. Where you see this kind of more star signal where the contributions are hovered around 0, that would say this variable is not very important or it's not being used very often. So in an aggregate sense, you can again figure out which of these variables are being used most often. You know, if we're forecasting rainfall, you would hope that the modeled QPF is being used by the random forest, and in fact, that's generally the case. You can't get tornado, hail, and wind where you don't have storms and rainfall. So again, that's a signal we like to see. CAPE and SIN and sea level pressure and 0 to 500 shear, again, variables we would expect. But we can also break down these contributions by time. Again, because predictors are gathered across the forecast window at different times, because the guest has 3-hourly output, we can attribute contributions per time. And I don't expect you to be able to read this, and I'll kind of zoom in on one of these plots. So this is the contributions of CAPE to day 1 hail forecasts. Really, we can see the diurnal pattern that we would expect, where CAPE is more important. These distributions are longer, they are wider around the diurnal peak of severe storms, and where our forecast probabilities are probably anchored. And all of this work is being done by our REU student, Hannah McDaniel, a sophomore at FSU, where she's kind of taken on this project to try to elucidate how we can better understand these forecasts in real time. And so we can aggregate these contributions, or we can just plot them on top of our probabilities. So we've started creating these real-time maps on a daily basis, where these black contours are our forecast probability of, in this case, day 1 hail, but we can also plot the contribution of CAPE at a specific time. So this is at 15 UTC, and if I iterated this forward in time, that up to 18 and 21 and 0, you could see that the CAPE contributions move northward, and you have this warm advection events across Iowa and Minnesota. And again, aligning with the meteorological intuition, but also telling us why these forecast probabilities are where they are and why they are as high as they are. and breaking down what in the environment is driving these forecasts. And we hope that in the future, this provides a little bit more confidence to SPC as well as WPC forecasters for our excessive rainfall models, and allows them to trust our products even more. Okay, I'll do a quick summary here. So for our new system that we've been developing, we have similar skill to SPC at day 1, but there is a skill gap at day 2 and day 3 where we can start to show that the machine learning products have value at those ranges and even beyond. And the skill at day 4 to 8 is really a result of the fact that we have continuous probabilities, and the random forest can issue probability contours less than 15%, where a 50% probability is maybe really hard to delineate severe weather events, but a 5% probability is a better, more accurate representation of that. And then we have these interpretability metrics that really are at their infancy for us, and we're starting to explore these, but there's a lot more that we need to dive into to really understand how these random forests work and how we can provide these forecasts and provide confidence to forecasters for their use. And I'll mention this last point too, because these products are going to operations, because we want forecasters to use them, even at local AWS offices, we really want this constant feedback and discussion with our partners to tailor products to their needs. For instance, if we're going to explore day 9 and 10 forecasts, which I will mention are not in the plans at the moment, but day 3 individual hazard forecasts are, and that's something that SPC specifically asked of us, and we were able to generate new products to inform them whether they want to move towards that in the future. And I'll just highlight this one example where we published some of the performance metrics out on Twitter, and we had a discussion with an SPC forecaster on social media where we learned that our products were actually used to help upgrade a day 3 guidance product, which is extremely helpful for us that, one, they're valuing our products, but this constant communication also allows us to improve our products. Last I'll mention, we have real-time data on our web. If you're unfamiliar with that, you can go to that website. I'll kind of show that in just a second. We have lots of experimental forecasts too. If you look through our excessive rainfall models, we have the ones based on GEFs, but also models based on our HER, based on the Nisselwolf model. We also have a blend of those, and we have verification statistics that we're producing. Again, all experimental, nothing that is actually in operations at the moment, but you can peruse those at your discretion whenever you want. And if you're interested in the actual GRIB2 files to have on your local computer, we have a public facing server that we can provide to you if you want to grab those as well. Just reach out to myself or Russ and we'd be happy to talk about that with you. So with that, I'm happy to take questions, and thank you all for your time. Appreciate it.